She did. She emailed me. All right, so yesterday we started this sort of introduction to what does it look like if I actually graph a sine function or a cosine function, and then we also have the tangent function on here too. But our focus today is how do I graph a sine function or cosine function, and then also how do I graph transformations of those functions. And then we're also going to talk just a little bit about the type of function this creates. It creates something called a periodic function. Periodic functions go through cycles, and every cycle is considered a period for those periodic functions. Periodic functions also have something called an amplitude. Well, at least these ones do. Sine function and cosine function have an amplitude, which is, in this case, 1. You see that it goes as high as 1, as low as -1, but it never goes outside of that range, so its amplitude is 1. We're going to write some of that stuff down later, but we're going to start by looking at what do these graphs look like. Yesterday, we graphed the sine function. We noticed that at 0, if I plugged in 0 degrees or 0 radians, my sine value was 0. If I plug in 90 degrees or pi over 2, I get the value of 1. If I plug in 180 or pi, I get 0. If I plugged in 270 or 3 pi over 2, I get -1. And then when I get to 2 pi or 360, it's back to 0 again. And so this part of it, from 0 to 360, completes one cycle of the sine function. You can see on the negative end, if I go -90, my output is -1, or negative pi over 2. If I put in negative pi over 2, I get -1. If I put in -180 or negative pi, I get 0. If I put in -270 or negative 3 pi over 2, I get +1. And all the way down to -360 or -2 pi, I get 0 again. So you can see here's another cycle of this periodic function. What we're going to do later on today is say, well, what if the period of this function changes? Let's say instead of going through one cycle in 2 pi, I go through a whole cycle in 1 pi. What's going to happen is all of these points will compress by a half. And so instead of being at pi over 2 in 1, I'm going to be at this quarter pi 1. And then the point at pi 0 will be at half pi 0. And everything will compress down to create a more, it's going to look like you go through more cycles. It's going to look like it's moving faster, if you want to think about it that way. But this is the parent function for a sine function. Okay? On the next page, for your homework, you were supposed to create the table and sketch what you thought the graph looked like. You should have something that looks like this. At -90, you have an output of 0. At 0, you have an output of 1. And in between there, you basically should see some points that are somewhere between the 0 and the 1. You have the half, the 0.71, and so on. At 90, you're back at 0 again. At 180, you're at -1. At 270, you're at 0. And at 360, you're back up to 1. And so you can see that your cosine function looks exactly like your sine function, except it's going through one cycle, still in 360, but its cycle, if you look at just the positives, starts at its maximum, goes down first, and then back up. Or you could look at it like if I shifted back by 90 degrees, it looks exactly like a sine function. Starting here, going up first, back down, and back up. And then I can finish out this graph by going left further. The -180 would be -1. -270 would be 0. And I'd be at my maximum again at 360, just like at positive, or at -360. This should have been a negative there. At +360, I'm at my maximum, and at -360, I'm back at my maximum. So you can see this is a periodic function, but it's a little bit different than the sine function in that it sort of starts, if you want to think about starting point, like its y-intercept is in a different spot, but then from there it goes down first and then back up. That's what your cosine function looks like. If I was to graph that against radians instead of degrees, it's going to have the same exact shape. The reason we're doing this is when we talk about sine and cosine functions, generally, we are going to be graphing using radians, not degrees, but I think it makes more sense to start with degrees because most of you are more familiar with degrees. Okay? But once you're familiar with, 90 degrees is the same as pi over 2, then you can just transition that graph down. Okay? Any questions on that so far? Okay, what am I going to expect from you? I'm going to expect that you can identify and graph these parent functions without using a calculator. Possibly if you need to look at your unit circle, you could do that. So how could I graph this without having a calculator? Well, you could memorize it. Cosine of 0 starts at 1. Or if you look at your unit circle, can I borrow yours a second? Cosine, remember, is the x value. So cosine of 0 is 1. Cosine of 90 is 0. Cosine of 180 is negative 1. Cosine of 270 is 0. So you can, and then you could keep going. So you could get all of these values right from your unit circle, but you will not be using a calculator. Does that make sense? Okay. Okay, we are not going to graph the tangent function today, but we are going to, on the next page, summarize some of the key concepts of the sine and cosine function. And this is just for the parent functions, because you guys remember every single function family we've dealt with, we've done transformations. We've multiplied by something. What does that change? We've shifted left or right. We've done a whole bunch of vertical shifts. Okay? But for parent functions, the domain for sine and cosine is all real numbers. And that's for both, so I'm not going to write it down twice. So you can plug in any x value you want. We just generally are going to look at those quadrant angles, 0, pi over 2, and so on, because it's a little bit easier to work with. The range, though, look at those graphs. What were the y values for those graphs? Yeah, anywhere from positive 1 to negative 1. I'm going to go negative 1 to positive 1. But not outside of that. Not for the parent function. Not unless I stretched it or shrink it. And so the range is from negative 1 to positive 1 for the y's. And that's for both functions, again. So I'm not going to write it twice. If you want to put that in another way, the minimum is negative 1. The maximum is positive 1. So then that gets at something that's a new term for you, amplitude. Although you might have done some stuff with amplitude in science classes, okay, when you're talking about frequencies and stuff. Amplitude is half the distance from the max to the min. Or you could say it's the distance from the midline to the maximum. In this case, our amplitude equals 1 for just the parent functions. Again, if we stretched those graphs, so then instead of going up to positive 1 and down to negative 1, we went up to positive 2, down to negative 2, then our amplitude would be 2. What was the period for the sine and cosine function? So I said a period is how basically the length it takes on the x's to complete one cycle. What was the period for that? When did it start to repeat again, basically? 0 to 360. So what we say for the period is that the period was 360 degrees, or if we're talking about radians, 2 pi. And that's the same for both the sine and cosine, so I'm not going to write anything different. They're both the same. Now where they are different is when we start to talk about the x-intercepts. Elliot, if you could look back at your graphs for the sine function and list off what are the x-intercepts in radians, please. Like where it crosses the x-axis.
Okay, negative pi, 0, pi, 2 pi, negative 2 pi.
And then if I went, negative 2 pi over there. So negative 2 pi, negative pi, 0 pi, 2 pi. If I kept going, would it cross at 3 pi? And 4 pi? Yeah. And same thing on the other end. So basically intervals of pi every time it's on the x-axis, if you think about your unit circle. The x-intercepts for cosine function, Cole, can you look at, do you have your paper out? Oh, you do. Look at the previous page and tell me what your x-intercepts were for the cosine function. Okay. Okay, good. And that continues. So those are, if you look at your unit circle, those are your points that are on the y-axis, pi over 2 and your 3 pi over 2. So every time you think about passing one of those points, you're going to be hitting the x-axis or x-intercepts. Okay, questions on that? Okay. Go to the back page at the bottom. And we're going to talk today now about transformations of the sine and cosine functions. Yes, so copy this down as notes. You should have some space. The second half of that back page has some space on it. So when we start to talk about transformations, what kinds of transformations we've done in the past is we've taken the whole function and multiplied it by a number. And that had some kind of an effect. What did that do when we multiplied a function by something? Stretch or shrink it in which direction? Vertically. Outside of the function, stretched vertically or shrinks vertically, exactly the way you would think. If the number outside is 2, the vertical stretches by 2. If the outside number we multiply by a half, the vertical stuff shrinks by a half. Okay? What else can we do? We could multiply the stuff inside with x by something. What did that do when I multiplied the inside by x by something? Shannon? Shrink or stretch horizontally, and the reciprocal of what you would think, right? What else can we do to functions to transform them, besides stretching and shrinking in both directions? Hank, think of something for me. We could, but we're not going to do that. It wasn't one of our transformations that we memorized. Yeah, we could subtract a number or add a number off the outside, right? And so that takes the whole picture and just shifts it down or up. In the case of our sine and cosine functions, if I was to take this function and just add or subtract, what's going to happen is my midline, which this is our midline right here, would just shift up or down. All the other points would stay the same, as long as there was no other transformation. Other than shifting up or down, which is what? Adding a number on the outside, right? What else can I do besides shift up or down? Add a number or subtract a number inside with x, and that shifts it left or right, opposite of what you would think, right? And so in our notes, what we're going to do is talk about, what if I took the sine function y equals sine of something, and I multiply the outside by a, and I take the stuff inside, which is usually x, and I subtract something from it, and I multiply by something. And then on the very outside of my function, I add k. This would be like if I made every single possible change. A multiplies on the outside, subtract something or add something to x on the inside, that's my horizontal change. multiply that x stuff by b. Notice this b is inside the sine function. If you were to think about which part of this is like your operation of what's inside with sine, it's the part I just boxed in. Sine of b times x minus h. And then the plus k is on the outside of that. That's our shifting up or down. So we could also write y equals a times cosine of b times x minus h plus k. In either of those cases, if you want to know the amplitude, you can just look at the absolute value of a. Whatever you multiply by is going to stretch or shrink that graph. Normally the amplitude is 1, so it makes it very simple that if I just multiplied that by 2, then our amplitude is 2. If I multiply by a half, now my amplitude is a half. If I multiply by a negative number, we didn't talk about that yet. What happens if I multiply a function by a negative on the outside? Who remembers? Cole, do you remember? Kind of makes the whole thing negative, but what does it do to the graph? Like, think about it, the picture of the graph. Like, if it was a parabola opening up, other way, over the x-axis. So instead of opening upward, it opens downward. That's if I do a negative on the outside. Okay? And so, anyway, that's why they had to put absolute values around the a, because if it was a negative, the amplitude doesn't become negative. Amplitude is a distance, and so it's always positive. The period is usually 2 pi. But if I multiplied by b on the inside, multiplying by b is going to have the effect of dividing my period by b. So the new period will be 2 pi divided by, we should also put absolute values around the b just in case they try to trick us and use a negative. We're dividing by whatever the positive b value is. And that will get us our new period. Something called a phase shift, which is really just a horizontal shift, occurs. What number here, I should say variable, what variable here is doing my horizontal shifting? Tori? Not the k, because the k is on the outside. Outside affects the y's or the vertical plane. No. I think you're thinking a reflection, Cole. It's the h. Horizontal shift h units. And that one is, remember, we think about it sort of opposite of what you think. If you see a minus in your function, you're really going positive h units, so you're going to the right. So if you want to write that down, x minus h means go right h units. If you have x plus h, you go left h units. And then lastly, we can have a vertical shift. Well, it might not be last because I should write down the reflection thing we mentioned, but a vertical shift, we said, is the k. If k is positive, we go up. If k is negative, we go down. And then the last thing, we mentioned it, let's write it down. If a is negative, we reflect over the x-axis. And we are not going to deal with, in this class, flipping over the y-axis. But if you were, how do I flip over the y-axis? Who remembers that? Remember? Yeah, sort of. You replace x with negative x, and that flips over the y-axis. But we're not going to, I don't think we have any that we're going to do that with. If we do, it's an accident. Okay? We're going to use all that now. Keep it handy. You're going to need this paper from me. We're going to start out by determining whether a function is actually periodic or not by looking at some ones that are not sine and cosine functions.